Okay, hello everyone. Today we're doing this problem about probability and the inclusion-exclusion formula. Uh, and I stumbled upon this problem while uh, reading the statistics problem of Oxford Notes preliminaries, which I find really interesting. Uh, Statistics and probability, sorry. And today we're going to try this. Okay, so first of all, uh, the inclusion-exclusion formula refers to knowing the probability of union of of events. So the usual of two elements is that the probability of A, oh, this is to be, the probability of A union B is equal to the probability of A plus the probability of B minus the joint A union B. Well, A and B. And this is shown like for consider the Venn diagram. If you add A is this whole, B is this other whole, but you've summed this part twice, so you have to subtract it the joint. So it's A plus B minus the joint, and then you have the whole union, which is this sort of tip 8. Now, this isn't the correct. Okay, so really this formula is not needed for now for this for the first part. You could do it like uh, looking at the problem. You will have. Okay, so let's read the problem. A confused college porter tries to hang n keys under n hooks. He does manage to hang one key per hook, but other than this, all arrangements of keys on hooks are equally likely. Let A of I be the event that key I is on the correct hook. All right. So all P sub I sub 1 would be, you've got the n keys and up to n. So, and you know that this one is correct. And this is Q1. And then you will have that for any of this number, it could either be maybe key n minus 3, and then here key 4, and then n minus 5, for example, whatever. So this rest of n's can be any combination, permutation really, because order does matter. It's not the same putting the key n minus 3 here than putting it here and then 4 here and vice versa. So the order does matter. Therefore, it's permutation. And how many ways are there to permute n minus 1 elements? N minus 1 factorial. So these are the ways to arrange the n hooks, the n keys on the n hooks, such that the first one is correct. The others could be also correct, but as long as the first one's correct, then there's n minus 1 factorial ways. And how many ways are there to arrange the n keys? There are n factorial. Therefore, probability of one single key is equal to n minus 1 factorial over 1 factorial, which is 1 over n, because n minus 1 factorial, n minus 1 factorial. Theta. Now, why would the joint of two keys be n minus 2 factorial? Well, it's pretty, it follows the same reason. If you got AI and AA, then um, for you will have that two keys. Okay, let's move this here. Well, copy it here. Copy, paste. You will have that you choose the first one or anyone, any any position, and that's fixed. So this one is 1, 2, 3. So this one is 4, and this one is anything else, n minus 2. So this one is fixed, and it's correct. So now you have n minus 2 elements left, because this one and this one cannot change. Therefore, it's n minus 2 factorial over n factorial. Okay. Now, the second sum on the right-hand side above is over all pairs ij, which satisfies the condition, write down the number of such pairs. Okay, so this one is, from here on out, I have not, this is completely new. I'm going to try things. So let's see. Write down the number of such pairs. Okay, so this is, you have two elements, I have j, and for how many of how many ways do you have to choose two elements? It doesn't matter which ones, such that, well, how many ways are there to choose pairs of elements? Since I of j is equal to ji, because this one doesn't exist if this, because you're considering the graders, you cannot say, for example, choose the position 1 and position 3, and then choose position 3 to position 1. That doesn't work. You have to, you can think about like these two are the same, so you want the 1, 3, not another pair and another pair, because as long as it's not 1, 1, this this subset will represent this one. And now, how do you count these subsets? Well, that's a combination. So you will have, there are n possible options, and you choose groups of 2, an order. Therefore, it will be n choose 2, which is n factorial over 2 factorial, n minus k factorial, n minus 2 factorial, which is k in this case. And you can also look it such that for example, not choosing the positions. So you want to choose in the first one and in the second. So the first one is n factorial, and then there will be a, so you will have to choose sorry, not n factorial, n, and for the next one, n minus 1. Since these are different, this pair will represent both. There will be, for example, if n is 1, then n minus 1, if you choose the first one for 1 and the second 4, there will be a duplicate when you choose 4 here and 1 here. Therefore, you have to divide these pairs by 2 factorial. Well, by 2, but it's the same as 2 factorial, because if there were 3, it would be 3 factorial. So you will have n times n minus 1 over 2, which is exactly the same as this one here. Now, let's do number 3. By generalizing the ideas in A and B, find the probability that at least one key is in the correct hook. Okay, so literally now we can use this one. We would like first to find the probability that at least one key is in the correct hook. It's literally the same. So we know that it's this formula, which represents the join, like the union of the probability of unions of uh, 2 or more elements. So let's see. And this is first how many ordered pairs there are. So this is n because you've got n keys. So it'll be the probability of the unions I in I of A sub I is equal to first there are n times, since all probabilities are equally likely, pairs, triplets, or anything, of P of A sub 1, A sub I, because it's the same for any, which would be n times n minus 1 factorial over n factorial. Now, minus the probability, like the number of pairs, times the probability of a pair, because all of these have the same probability, since they're all arrangements are equally likely. Therefore, this will be how many ways to choose pairs? We've calculated that in B. There are n choose 2. So we will have minus n choose 2. And what's the probability of a single pair? We calculated that in this n minus 2 factorial over n factorial. 2 factorial over n factorial. Now, plus triplets. Triplets, it's a new one, but we can use the same ideas for this. We want how many possible triplets there are, and since all triplets have the same probability, then it will be the probability of 1 times how many triplets. The probability of 1 follows the same idea. You fix 3 points, 3 keys, and you rearrange the rest, which is you permute the rest, which are n minus 3 factorial over n factorial, and you choose from n, you choose 3, and therefore so on and so forth. A plus minus 1 and choose n, because you reach up until n of 1 over, well, n minus n factorial over n factorial, which would be how many ways are there to arrange n elements? There's only one, because well, sorry, there are, okay, I think I've made a mistake somewhere. I think I've made a mistake, because yeah, for this it seems like you want to divide by 2 because you only represent 1 with I of j greater than. However, here, here it, well, isn't that one, that's how many ways do you have to arrange the n elements? I would say n. Okay, I stopped some time and took a rest because I was getting nowhere, and I'm not in a hurry just now. Okay, I think we were on the right track, but not quite. Okay, I'm thinking about if you've got are correct ones, this means that if they're correct, there's only one combination such that all of them are correct, and that's this one combination. Now you want that the next n minus r elements are all incorrect. So you want this one is wrong. You want not a 1 and not a, well, let's suppose this is 1, like this is the 1, although it's n minus r, n minus r plus 1, n minus r plus 2. Let's consider this a sub 1, not a sub 1, and not a sub 3 for this specific case. However, we don't know how to do the join of these three events. However, if we consider the conjugate of this, we can use De Morgan's law to notice that this is this union A3. And if we want to take the probability of this, it will be U1 minus the probability of this, of the conjugate. Now, do we know how to make this? Yes, we can use the formula we've just used before, which is 1 minus well, yeah, I think this is where I'm getting confused. I'm mixing probabilities with possible outcomes. So here, what we want, honestly, is possible outcomes. And then all of this divided by n factorial, which are all the possible permutations. So instead of looking at probabilities, we're trying to look at how many are there. And then will be n factorial minus the number of these elements. And then all of that over n, well, not n factorial because we have only 3 elements, n minus r factorial. Okay, so for any to be correct, you just need one to be correct, the other doesn't matter. So you have 3 possibilities. Well, 6 possibilities. This one's correct, this one's correct, this one's correct, these 2 are correct, these 2 are correct, all 3 are correct. Okay, how do you do that? Well, we can probably work this like, how many are there that these are correct? It's 1, and then the others don't matter. So it will be 1 times n minus r minus 1 factorial. Now the next, and that is for 3. Does that really matter? Okay, so this is, given that this is correct, this one can be either way, which I think it's almost done. You just need to account for this one to be incorrect and subtract when this is all incorrect. Like, yeah, all incorrect, which would be considering this is incorrect. So another 1 times n minus r minus 1 factorial, and minus 1, which is when all of them are incorrect. So let's see how this could be done. I'm not quite sure this is completely correct. I think it makes sense. Like, you've got, this could be any combination, as long as there's one correct. Okay, if here you've got that there's one correct, then this could be any. And if this one's incorrect, as long as not any of all of these are incorrect, which is only 1. Yeah, I think this makes sense. So now I have that n minus r factorial, which has all the possible ways to arrange this, minus 2n minus r minus 1 factorial minus 1, so plus 1, over n factorial. I would consider that this would be the probability of n of r exact. I think. Well, not quite because, or yes, because here I'm taking for r element and then, and no, yes, I think this is correct. Is this the same as the equation? S- Um, um, I mean, it does not look like it at all, but let's see. There is one combination of all correct, and then n minus r minus 2 and minus r plus 1 combinations of all of this being incorrect. So that's literally exactly our elements, right? Let's divide this. If you've got n minus r factorial, then that means that this is uh, n minus r times n minus r minus 1 and n minus r. No, I cannot show that properly. Mm, 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 mm. I'm not sure if this is correct. It could does make sense. Okay, I will ask ChatGPT. I know I don't really like to use it, but I don't know if there's any other way to answer this. Like, yeah, I know there has to be another way because it doesn't look like it's the same, but I want to know where's my mistake. I'm sorry for you that I'm just that useless. Um, mm, mm, mm. Let's try copying this. Um, I'm just gonna pause and then okay, I've already consulted it and we were almost there. It's just that this reasoning is incorrect because um, I'm not counting mm, certain cases. Like, I don't exactly know why this is incorrect, but I know why the following reasoning is more correct, which is not the best, but it's better than nothing. Okay, let's delete this, and I will. Uh, okay, so uh, if we want the probability, then um, the number of the arrangements, like we say here, it's then okay. It's very similar to the first few steps of this exercise. We want first how many ways to arrange one correctly and 2, and 3 correctly. Because if you want the probability of this, it will be just the number over the the amount. So we know that the probability of this A1, A2, or A3 is equal to the number of combinations of that over how many there are, n minus r factorial. So we want the number, we can calculate the, the probability and multiply it by the number of options. How many options do we have? Well, the probabilities using the inclusion-exclusion formula. So we have, for the first element, we said fix the first one. Well, for the probability of a single one being correct is fix the first one as correct and do the next and have the rest of the elements over n minus r factorial, which are all the elements. So this is the probability of 1. And how many ones do we have? We have n minus r, n minus r. And if you look carefully, this is equal to 1, real, actually. But so far, let's keep this going. Now, what's the probability of this? Okay, according to the formula, it's now minus the joint of two elements, which, what was the probability of a pair of two elements? N minus r minus 2 factorial, because you fix 2 and the rest you don't care, over n minus r factorial. And how many ways, how to arrange two pairs? N minus r, oh, choose 2. And so on and so forth. It will be n minus r, choose 3. This is a minus, sorry. Plus n minus r minus 3 factorial, n minus r factorial. Okay, and so on and so forth using this formula. Now, we can notice that they are these choose these combinatory numbers are mm, the expression is n minus r factorial on top. Let's clean this. Okay, so for this one you will have n minus r factorial over n minus r minus 2 factorial times 2 factorial. So you will notice that this simplifies with this and this with this. So you will have this is equal, the probability is equal to the sums between I equals 1 up until I equals n minus r, because you will do this n minus r times up until n minus r, and then 0 factorial over n minus r factorial when you fix all the elements and you only have one correct way. And this, therefore, since all of these are 1 and just leave the number below factorial, it will be 1 over I factorial. And this, since the sign changes for each iteration, you will have minus 1 to the k plus 1. Because the first one is positive, so if, well, I plus 1. Sorry, and let's move this bit here. Okay. Yeah. My minus 1 here to the I plus 1. And of this, you have to multiply it by n minus r factorial and divide, and this is the number of ways to arrange this. Now I have n minus r factorial minus all of these combinations. Therefore, I think it's n minus r factorial minus n minus r factorial times the sum of I equal 1 up to n minus r of minus 1 k I plus 1 over 1 over I factorial, and this is equal to the number of ways to arrange exactly our elements correctly. So number of exact r. So now if we divide this by the whole combination, which is n factorial, we will have exactly this, not quite, not exactly, but I think I know why is that. It looks really similar. That's true. Mm, okay, so you can have common factor n minus r factorial times 1 minus this sum I equals 1 n minus m minus 1 I plus 1 over 1 over I factorial. And if you want to add this 1 and then change this sign, then you can take this one out because then all the signs are changed. This is a plus. And since the first element we want it to be a 1, then if this starts at 0, then this will be 1 plus, now the next element will be minus 1, which is what should be the first element here, because it will be 1 minus I equals 1, this is 1, 1 minus 1, the first element, and then so on and so forth. Therefore, this changes to this. And all of this over n factorial is equal to g of n of r, which it's rubbing me the wrong way because does this equal 1 over r factorial? Not really. No. It's more like 1 over n choose r times r factorial. But if I like, it's really similar. We have literally everything except this r factorial. And what's bigger? 1 over r factorial or our number? So let's see. Is this an overestimation or underestimation? If I multiply by r factorial here, then I will have n minus r factorial. This will be 1 over n choose r. Should be like multiplying this by n choose r works as fine. So I'm pretty sure that this is because here we haven't chosen our r's to be any r. Although Um, yeah, like we have just taken mm, a set of R numbers, but not any set of R numbers. So I'm pretty sure it's that we're missing choosing n and choose R elements, and that will give the correct equation because it's n factorial over n minus r factorial times r factorial times n minus r factorial over n factorial times the sum of I equals 0, n minus m minus I to the I 1 over I factorial. And this goes with this and this with this. And yeah, I think that's it. Wait, this, and beauty more nicely. One. That little detail is not something I liked much, but it just happens because I have the solution. But yeah, I don't think I want to do much more about this problem.